Okay, maybe we can get started while these guys join. Do you have anything to show me, Jay?
Yeah, I did the CPW ground simulation. I just share my screen.
Yeah. Okay, walk me through what you have done.
Sorry, I couldn't figure out how to unmute myself. Yeah. Uh, I tried making the ground planes very big, but that didn't have a huge effect on. I mean, it was still quite reflective. And then except that, it's mostly same thing which we did in class. I added the vias, not the air bridges.
Okay.
The response here is still not great. I was wondering, do these vias add any capacitance of their own, or is it just negligible?
Well, they shouldn't do too much, and they're anyway.
I mean, would it be
rel-
of some merit if they're at an offset in some sense to each other?
Offset from where?
I mean, uh, this seems like a capacitive unit together, so you know.
No, it's too far. There's also a conductor in between. It's too far.
Okay.
Don't think that's going to do anything. But your VS look a little irregular. It's fine. But did you check whether the system is behaving like a transmission line of a different impedance or is something else going on? I mean, could you adjust its properties to make it closer to ideal response?
I haven't checked that yet. I'll do that.
Okay.
I just done this.
All right. What about you, Srijita?
Yeah, I tried. I'll share my screen. This is the one I constructed. I used these parameters and 50 ohms and 90 degrees at 6 and my response was like this.
Oh, this looks much better. What did you change? And go back to the parameters again. So width is 280, gap is 60, right? Thickness you used to 1 here, but anyway, that shouldn't matter. Huh. Show me the enclosure. The dielectric layers tab. Okay, and zoom into the drawing and show me the dimensions of the center line and the gap.
Yeah. 60.
Yeah, use the measurement tool and
The gap
yeah. Okay, and the width.
280.
80. What was the TX line number? 60 and 280 or
Uh,
yeah,
yeah, this.
it's interesting. Jay, what was the numbers you had used?
Uh, just check.
Let me also see what did I use.
Will I stop sharing?
Yeah, sure. Good.
Okay.
So my gap is 50 and the width is 100.
Oh, Srijita, did you have a ground plane or no ground plane? You had a ground plane, right?
Sorry, I was muted. Yeah, I had a ground plane.
It's a bit strange. Let me open up TX line because her gap is 60, right, Srijita?
Yes,
And your
60.
center line width is?
280.
So how can this be so different? Did we like calculate it incorrectly in TX line? Let me check again. Share my screen now. Six gigahertz, 90 degrees, 60, 762. Okay. Oh, that's the problem. Yeah. Okay, this makes sense. So, in fact, what we had done yesterday was slightly wrong because of this thickness being much higher. See, what happened was initially I had shown you a big CPW with big features and big gaps. And then we went to a smaller one with only a gap of 50 microns. And when you have such small gaps, then a thickness of 35 microns of metal actually makes a huge difference. Remember earlier for microstrip, I had said that this number is not really consequential, and that's true. But for a CPW with a very small gap, I mean, basically consider now that there is a 50 micron gap and 30 to 35 micron height of the metal. Now that gives you a lot more capacitance per unit length, right? Because it's now there is a third dimension which is bringing the ground and the center conductor together. So correspondingly, the numbers we ended up having for a 50 ohm line was just wrong. Because in microwave office, the simulation, electromagnetic simulation essentially is for finite, basically zero thickness kind of metal simulations. And the thickness is only present indirectly as a way to compute the loss. So while this was 50 ohms, this was actually not correct at all. So I don't know whether accidentally or by choice, Sridhar chose the 1 micron thickness because that's the default number and ended up
By
getting.
default, yeah.
Yeah. So that ended up giving the correct dimension. I was actually very surprised yesterday because I've never seen this kind of mismatch between TX line and the anticipated thing. So that was the problem. So now when you calculate it for the correct, it's like a much smaller thickness. And normally in like on chip circuits where you have small gap CPWs, you end up with film thickness of only of about 100 nanometers or so. So even 1 micron is actually a lot. But at this level, it should stop making a huge difference. You see, now it's not making such a big difference. So this is good. Okay, so this now makes a lot more sense. If we, let me adjust this now. So this should be 60. and 170. Let's get rid of this. Right, let's see. This works. Anyway, while it's running, I hope the what happened is clear, right? I mean, you really have a three-dimensional situation, and if you have a lot of height there compared to this dimension, then obviously the intermetal capacitance is going to be much higher. So that's actually affecting the overall impedance of the device. So this general notion that this thickness should be usually much smaller than gap for typical circuits, and you'll usually not make 100 micron gap or a 50 micron gap kind of transmission line for standard circuit board uh, things which have fairly thick copper on them for getting good conductivity. It's usually much more widely spaced. Okay, still running quite slowly. All right, but it's already basically getting similar results to. In fact, now we can see whether the via holes are helping or not. So that's why nothing we changed yesterday was actually helping this, because we were just off because of the thickness. All right. Anyway, that green line is the comparison one which we had made. So this is fine. Let's freeze this and go back and get rid of. Anyway, this was a accidental good lesson, but one needs to be careful about the thickness as well. So the simulation microwave office does sort of is quasi, it's a 2D kind of simulation. The third dimension is not really taken into the picture fully, and that's why this thickness parameter cannot be specified except for as a mechanism to compute losses. But if the dimensions are not compatible, then you're going to get wrong. So okay, didn't make a huge difference, but this is in fact looks better without the vias at least in this range of frequencies. That's not too surprising, given that the transmission line is not very long. Okay, so that typically is the case. The effect of mismatches will only become apparent when the length of the transmission line is comparable to wavelength or several wavelengths, and then you see the reflections sort of setting up something. Otherwise, for very short lengths of transmission line, you will not even see the difference. So what I mean is that if you have, say, 250 ohm ports on two sides, and in between you connect a piece of transmission line, it's very, very small. So L is much, much less than lambda. It really doesn't matter what the impedance of this line is. Unless it's like a short circuit or a completely open circuit, the transmission line, as I said, in practice, will be somewhere around 50 ohms only. So it will not make a huge difference in the transmission and reflection as long as it's very, very small. Okay. Small in length compared to the wavelength at which you're operating. So, okay. Then Joydeep, do you want to share your screen and show us what you have, if you have anything?
Yes, okay. Can you see my screen?
Yeah.
Okay, so this one. So I took 35 micron thickness. So
okay,
I was
so
getting
yours
some
is
loss.
also off. Yeah. Not loss. Your return loss is not very good. That's what.
Yeah. So there is some great mismatch. Large mismatch, like 40.
Well, now we know that the thing you have designed is actually going to be of higher impedance than 50 ohms, because the gap is larger because you calculated for 35 microns, whereas in this EM simulation. So remember yesterday I was telling you, from the return loss, you cannot tell whether it is above 50 ohms or below 50 ohms. Because you can go,
Okay.
so take your tuner and make it cross 50 ohms, and you will see that again you can match it up, right? Because the return loss is going to go to minus infinity at 50, and then it goes up in both directions. So by just looking at the magnitude of the dB loss, you can't really tell whether the you're figured out the correct reason for the mismatch. So for that, you need to do something else. So maybe I can show you now. So you can stop the screen. Can I just look at your EM structure?
Yeah.
It looked like you had put a very high density of vias. Okay. Okay, great. All right, you can stop sharing now.
Yeah.
Are you able to hear me clearly? It's giving me some message that my internet connection is not stable.
It's some patchy.
For me, it seems clear.
Okay. Anyway, if it gets bad, just let me know. Right. Okay. So I guess probably easier to do it with a schematic, so that you don't have to wait for the simulations to run. So, right. So here we had 250 ohm lines separated by 90-degree length of, let's make this.
Should I
6K.
stop sharing?
Yes, please. Okay. So sectional transmission line 40 ohms, 6 gigahertz, 90 degrees at 6 gigahertz. Let's just look at this graph here. Schematic one. I've already said that the return loss is not such a is it calculating it again? Oh, okay, because I had Vias back. Anyway, I think that can run in the background. So yes, okay. So this is minus 13 dBm. If I make it larger than 50 ohms, also you will get something which is sort of similar to that. From this, you can't tell whether the transmission line is lower or higher. So for that, you can look at Z in, for example. And let's say, look at just the magnitude of that. And now you see that it's 50 ohms, close to 50 ohms. It's saying it's close to 50 ohms at 50 as at low frequencies. And this is basically the consequence of the length not being long enough at low frequencies, right? So this is 90 degrees at 6 gigahertz. So as you go to lower and lower frequencies, this electrical length is not, the physical length or the electrical length is not comparable to the wavelength at that particular frequency. And hence, essentially, it just sees the other 50 ohm port on the other side. So that's what you're looking at, right? Input impedance is basically it's combined impedance of this object from the perspective of this thing. So it looks like 50, and then it goes up, and then it comes back down. If you actually looked at higher frequencies, you will see a repeating pattern. So outside of this, the reason this is again looking like 50 ohms is that now some kind of an impedance transformation is happening, because that section of transmission line is transforming the 50 ohms here into something which is close to 50 ohms. So it looks like it's matched to 50 ohms. However, if you now, let's go back here. So it went from, let's say, above 50 up to some value and then back. Let me freeze these traces. Now, if I make it somewhat closer to 50 ohms, but still on the higher side, then you see it again goes from 50 a little higher and then back. So now only if I go lower, it goes in the other direction. Okay, so this is how you can tell whether the, so if the problem is that you have 250 ohm ports which are connected by a transmission line, an ideal normal transmission line, except its impedance is not 50 ohms. So the way to figure out from a measurement like this is to look at the Z in as a function of frequency, and then it should basically, if it is lower, then the value of the impedance measure will always be on the low side below 50 ohms. And if it is higher, it will be above it. So we can actually increase the electrical length here to exaggerate this effect a little bit. So let's go to 360. Then we should see many of these wiggles, right? So there's always a special frequency where it matches, right? And then it goes to lower value, matches again, goes to lower value. And if you're the other side, you get the opposite behavior. In fact, you see the matching points are the same. It always transforms it correctly to 50 ohms at that particular point. You can think about why this happens. And the amount of deviation, like from 50 up to this value, which gets to 71 there and something like 32 here, depends on how much is the mismatch. So it's not this number clearly, because here it's 60 and it's going up to 70, because again, this is some kind of impedance transformation going on. And remember that we are only looking at the magnitude of the impedance, right? So that doesn't really tell us the gamma. The gamma is related to the complex reflection coefficient. So this is as the magnitude is close to 50 ohms. So instead, if we actually plot, let's say, the real and imaginary of this, And let's do this. Duplicate. And you do see that at the matching points where the impedance magnitude was 50 ohms, the imaginary part is actually 0. So it's purely real, which means that gamma is 0 at this particular point. Okay, so that's how you can check whether the transmission line is higher or lower impedance than 50 ohms by doing a measurement like this on. Of course, if you're doing it on a real, somebody gave you a little box with two connectors that said that there's a transmission line inside. Tell me what the, whether it is lower or higher than 50 ohms. Then by looking at Z in, you can do that. Okay. So, okay, that was that. Now, let's see. So we did this strip line, you guys did on your own. Coaxial, we can't really simulate in microwave office, but here again, it's very simple. There's only the center diameter and the gap between the center and the output. So it's kind of like a folded CPW, or you can think of the CPW as a cut coax. This again has ground uniformly all around it. So this has a nice TEM mode. And then you have this slot line mode. This is basically just a 2-conductor transmission line. Somewhat rare to be used. It usually comes up in as some sections of transmission line in a bigger network. It's not a very commonly used thing because, again, the ground planes on either side are sort of assumed to be, extending to infinity. Of course, in practice, we can do that. But we can try to set up this simulation, and I can show you. In fact, I've not tried this in a long time, but I can show you another type of excitation port which microwave office allows, and we can see if that works here. Because the problem is there's no ground as you typically expect. Remember, in the port, you only connected one thing, right? Even when you did schematics. So here, sorry. Here also you just connect only the center pin and the ground is sort of assumed to be present. And even in your electromagnetic simulation, you just connected the port to this point and the ground is sort of assumed to be present there. But in slot line, there is no such thing. So one has to be careful. One cannot use this kind of port. Okay, so let's see what we get for, so again, 6, let's say height of 762. And here it basically assumes there's no actual ground plane there. Though I would think that the presence of the ground plane would still allow this to be present, but now that includes complications because now there are 3 different conductors. See, this is plus and minus, and then there is, if you had a ground, then it would be a third conductor. It's not the same as here because here this ground, and that ground are assumed to be at the same potential. So there's effectively only 2 conductors. That is not the case here. Okay, it's a very subtle difference. I hope this is clear. Is there any questions about it? What I'm trying to say right now? Why there is no ground? In fact, this is related to the next tab here. I'll show you in a little bit. Okay.
Could you just repeat once? Could you just repeat that point once?
Which one? I can't, Jay, your voice is, you speak a little louder. You're sitting in a very noisy environment. I can't hear you.
I was a bit unclear as to why there is no ground. I didn't understand the reasoning.
Okay, can you tell me what you understood?
So in that, in CPW ground, we had a dedicated line in between, and the other 2 were assumed to be grounded, and with the base plate.
Yes.
And
so that means that effectively, even though there are on the face of, by looking at this schematic, it looks like there is 1, 2, 3, and 4 different conductors. Okay, but because the two grounds on the side and the ground on the bottom are assumed to be connected together, which is something we implemented practically by putting these vias, effectively there is only two conductors because this is all ground and then the second conductor is the middle one. So transmission line is always between two conductors, right? But here, there is no such assumption about these two things being at the same potential. In fact, they cannot. If they are the same potential, it's not going to support any transmission line mode between them. So this is like plus and minus. You can call the minus ground if you like. It doesn't really matter. Point is there are two conductors which can have a potential difference between them. If I now included a ground here, then I can't really make it appear like the same situation like the CPW, because now if I ground this one to this one, then it looks like some weird hybrid of a microstrip line, because this is a conductor and this is a ground plane, and then it's sort of the ground is on the top as well, so it's sort of a strange thing. It probably will support a mode. It's something one can test, but that is the reason why the slot line mode doesn't have any ground reference per se. And this is fine as long as the distance here is typically much larger than the gap. And that basically brings the same kind of argument we made in CPW ground, that if the gap is very small, then the presence or absence of the ground plane on this side starts to make less and less difference, because field lines never make it all the way here. This ground is quite close to it. So similarly, in the slot line, the ideal mode of operation is only these two conductors are very close to each other, and then everything else is far away. So even this dielectric is considered to be thick. That's the normal assumption. If you put a metal here, something else happens, and we will discuss that in just a little bit. So let me.
I have a small question.
Yeah.
So, yeah. So suppose we have two different kind of sections of transmission lines. One is slot line and another is strip line, let's say. And both have same characteristic impedance, let's say 50 ohm. If we just connect them together, then because the impedance is same, we expect no reflection, like it should be continuous. But if we think about the field profile, then one can have TEM kind of profile, another cannot. So can that cause any problem? Or
Yeah, absolutely. I mean, okay, it's not directly connected to the discussion we are having now, and that is a particular topic about transitions and things which I will be discussing later. Okay. But briefly speaking, just because two transmission lines are the same impedance, just by connecting them also has a very specific meaning. You're just putting them in contact with each other. It does not mean that that will be a perfect transition from one to the other. Let me give you a very simple example which will make it obvious that that cannot happen. We already know that CPW can be made in many different ways, right? This is a 50 ohm transmission line. Okay, now something like this is probably also a 50 ohm transmission line. Now, how will I connect it? Connecting it would mean that I just bring these things together and do something like this. This will not work because the dimension changes are too abrupt. So even though it looks like these are 50 ohms on either side, the joint here is going to develop some extra capacitance or extra inductance to ground. Capacitance to ground or inductance in line, and that will cause a reflection because the mode shape has to change. So it's a little bit more subtle than that. When we are working in the schematic representation, we don't think about how the the shape, the actual field lines are propagating. And this is particularly important in the whole issue of how do you take signals which are coming on coaxial cables, which is a different type of a transmission line, but it is 50 ohms, and you bring it down to a microstrip or a CPW on chip. We don't just connect the cable directly onto the PC board, right? We use a connector, and that connector is basically the transition. It gradually takes the original transmission line and slowly transforms it to a shape which is more amenable to the other transmission line. And this is something we had discussed earlier as well, that the correct way of making this transition from a big CPW to a small DPW is to do it, gradually. So then you can call this as your transition or your bridging system. If you do this properly, then it will not reflect. But you cannot connect two different types of transmission lines just directly. In some cases, it can work if they are somehow compatible, but in most cases, they will not work. Right? Even yesterday, we had discussed the transition of microstrip to a CPW by bringing the ground in, and then making this something like that. Right? So here there is no ground on the side, but here now the ground is on the side. So because remember, the mode is going from a situation where now I'm looking sort of at a side view, where in the microstrip, the field lines are going from center pin to the ground. Whereas in here, the field lines are going like this. So that transformation has to happen, and that has to be done gradually. So somewhere in this middle part, there will be field lines in both going downwards and also in sidewards, and slowly the downward field lines will go down and the field lines in the horizontal plane will increase. So that is necessary to do these kind of things. Okay.
Okay.
All right. Right. Back to slot line. So let's see what is. $73 ohms. In fact, this is another thing that I think with slot line, making a 50 ohm transmission line is also kind of tricky. So here it's now saying that G by lambda must be greater than some number. That's like the limit under which this typically works, but I'm not able to get the impedance to be close to 50 ohms in this regime. So here it satisfies that particular problem, but it doesn't. So I guess the way to do it is it doesn't put a constraint on H so far. So what will we need to make this impedance go lower in terms of H? Srijita?
For the impedance to go down.
Yeah, because go down. We are at 73 ohms and I want to go to 50 ohms.
50.
Huh?
Yeah.
Yeah. So what should I do? So gap, I'm not able to reduce, that much. So it doesn't, at some point it starts to complain that and it's also not really changing that much.
Increase the height.
Okay, so it fails here. So let's keep it at 70. Increase the height. Let's try. Yeah, it has gone down. But it went down. I almost doubled it. Well, or made it 1.5 times and it moved by like 1 ohm.
Yeah.
And look at the gap to height ratio. Do you think it's really going to help? This is so far away from this anyway. It's not going to affect the field lines here. So if I even make it now 2000, basically nothing is going to happen. It's now again complaining about this. All right. So that's it. We have no other option left. The only other option is to change the dielectric constant, right? That's the only other option we have, because we have height, we have gap, and then we have dielectric constant. So dielectric constant should be increased or decreased?
Decreased.
Huh?
Decreased.
Decrease to make this 50 ohms or closer to 50 ohms. Remember, you want more capacitance.
Sorry. Oh, yeah. Sorry. Then increase.
So you're getting closer, but again, it doesn't like this.
G by lambda something.
It's complaining that this has to be. So essentially, it's very difficult to get to a 50 ohm transmission line in a slot line geometry, but that's okay. Let's go back to this and whatever we have, let's say 74 ohms. Okay, so we can try to make a transmission line of 74 ohms using this. Let's see. Just duplicated that. That way we get all the enclosure properties and everything to be set. Now let's have two conductors. I'm going to get rid of the ports as well for now. Closer. Sorry, what was it? 100 is what we need. And how much is this? I think it should be okay. Let's try. Rest is of course same. The dielectric is we have 762. We have those two air things, but that shouldn't matter. As long as we don't put any vias, it's fine. Now the question is, how does one excite this kind of a transmission line, right? So for this, we'll introduce a new concept. It's called a differential port, because this is a differential transmission line in the sense that it doesn't have a ground. It has sort of plus and minus. And that is another reason why it is very difficult to launch a slot line from a coaxial connector. You have to do some weird tricks to make that. It's not impossible, but it's a little trickier. So this thing, in the draw thing, there is this thing called internal port. Okay, this what allows you to create a differential excitation. It can have complications. It's very rare to use these kind of things because of the ground reference not being there. It becomes tricky because for other ports, there is always assumed that you just connect one terminal and the other is ground. Whereas here there are two conductors. So which one it's going to use as a ground? As I said, it can be plus minus, or it could be called plus and ground if you like. But if you have a circuit, a network which has both the regular type of grounds and this type of grounds, then you can have some subtle issues. Okay. Now, since this is just a single piece of transmission line, we're going to go from one port to the other port. This shouldn't matter. And so we can try it. So the way to make an internal port is you need two conductors to be in contact with each other. Okay, so since there was a 100 micron gap, I'm going to put two 50 by 50 micron squares here. Okay, so these two, if I just leave it like this, this is basically a short. I've connected them completely. As I told you, any metal pieces, if they share their edges, they are assumed to be connected. Okay, if I just do this, this would be a short circuit kind of boundary condition. However, now if I touch this, like select one of them, go here, let's say add internal port, and then come to the boundary and click like that. then it creates a port like this, and it sort of gives this plus sign here. So that's sort of just a reference that it's assuming this one to be a sort of negative with respect to that one. Okay. So that's now an internal port. In a schematic, when this is used as a sub-circuit or in any measurement, you'll just see one port as one. Okay. Now we do the same thing on the other side, because this is also a differential. Not here. And you have now two internal ports in this line. And because this is supposed to be a transmission line of 74 ohms impedance, we will set the port impedance to be 74. Okay. Otherwise, it will not be fair to compare. So what we are saying is that let's try and launch with the 74 ohm port and see if the 74 ohm transmission line actually gives you good transmission through the system. Okay, I hope this is clear. I'm just, because I cannot make a 50 ohm line, I'm just moving my reference to a different thing. So I guess we can use this graph here. Let's plot EMS slot line. For parameters. Is 1. And S11. Right. Let's see if this works. Doesn't look great. Wait, did I? Okay, there's no thickness specification here as well. 74. Yeah, that shouldn't really matter. I haven't tried slot line in this form in a very long time. Okay, I guess we
He said the yellow there is the thickness is 35 micron.
that's what I went to check, but there is no thickness specification here at all in TX line for the slot line mode, because I guess it shouldn't matter. So I would have thought it would matter, because if this was thick, the capacitance per unit length would actually have it's not there as an option here.
What is the width of the rectangle compared to the gap? Is it
Well, yeah. So the first thing to check is whether the this needs to be much bigger. So we can try that. So this was what, basically it was around 500, right? So we can make it 1,000. I mean, I would think that shouldn't have made such a big difference because the gap is still pretty small. Maybe. We'll see. There's one other thing which I just okay, it did make a difference. So clearly it's not in the limit, but it's still not so great. So one other thing is the enclosure, right? The bottom side had this ground plane. Let's see if that is freeze this for reference. But this definitely improved things quite a bit. Otherwise, that it was going up to like -5. So I will make this approximately open. So that way it's sort of like a floating thing. Let's see. This improves it. It's actually made it worse. That's weird. It's really true. Just verifying this to see if it is repeatable. Sometimes these EM simulations can do strange things.
I have one question. So this here the port is that straight line that between the two small rectangles, right? The squares.
That's right.
So like if we define that as the port, then when it comes out, so after crossing the small rectangles, when it goes to the main slot line part, will it not face a abrupt geometry change?
It's a very good point. So this is exactly was going to be my next area of inspection to see if
Okay.
something can be improved. Okay, I guess it does. So that might be. Yeah, but I guess we should, strictly speaking, not have that ground and then try to improve it. Okay, let's try that. So if others didn't follow what Supriyo was saying, he's basically saying, well, okay, here is a port. Now this is some 74 ohm transmission line, but what is this thing, this 100 micron small object? Could this be like an impedance mismatch? Yes, it's sort of like a small wire, but it's not very big. And also it's so that what matters for such connections is the aspect ratio. If you have something like this, then there is a problem. Okay. But if you have, so assuming that left to right is the direction of propagation. However, if you have something like that and left to right is the propagation, then it's less of a problem because it's sort of low inductance path. And usually for wires, that's what one sort of considers. The distance is also very small. It's 50 microns, compared to the wavelength, it's very small. So because of the same reason I said earlier that it shouldn't matter, but this is one place to try. So because this dimension is fixed, the only thing we can do is try to make it wider, right? And this is all somewhat arbitrary because there is no such differential port which exists in the in real situations, except that you could have a device in here. And then this is a good question to ask: what is the impedance seen from the perspective of the device? And such slot line modes can be used, and there's actually a way to go from CPW to slot line, which I'll tell you in just a little bit. Okay. So let's try that. So if this is 150. Not really. It looks as bad as it was before. Let's try one more step and see if it actually is making it better or not. Double it again.
Why do we expect this to make it better?
I just said that before this, right? It's wide compared to its length. So this dimension is bigger. So now we're talking about signals going in this direction. So wide strip basically has low inductance. So what the presumption here is that there is now an effective inductance between the port and the rest of the transmission line. And this is sort of connected to the question which Supriyo asked earlier about going from one type to another type. So here this port is not really able to launch the wave correctly. Now, maybe there are other ways to do this, and I will explore that in just a little second. As I said, I haven't done this in a very long time, not remembering. I think, in fact, I might have maybe never tried to do it like this for a slot line using the internal port. But we'll learn together. So the idea is you're now trying to reduce the inductance. In fact, I will just discuss this idea separately using a schematic to explain what I'm trying to do here.
But making this wider, would it change the effective dielectric constant, which we used while calculating the capacitance?
No, it's not changing. It's not changing the transmission line. See, the transmission line is still this whole thing here, right? It's just how I'm connecting my port to the transmission line so that it matches perfectly. So there's something else. If this doesn't work, we will try something to see if the problem is got to do with actually an impedance mismatch between the port and the transmission line. Maybe it is not 74 ohms as we thought based on the TX line calculation. So we can check that in a very simple way. Let's 1 second. So it does seem to improve a little bit on the lower side. So this is partly the problem. Now let's try something here where I'm going to change the impedance here to something. Actually, why don't we measure that trick we just learned about looking at Z in. Okay, so it is showing similar behavior, and it's unfortunately showing this as 50 ohm. Now there might be a slight problem from the point of view of whether the calculation is being done assuming a 50 ohm reference. That could be an issue. But this seems to suggest that the impedance is going up, which means the impedance of the transmission line is higher than we thought, significantly higher. So we could do something where let's just try to change this thing here. I don't know whether it'll actually resimulate or not. Let's make it 100 ohms. In fact, this will tell us whether this number is even making any difference to the calculation or not. Right? If this doesn't change at all, then yeah, it didn't change. Okay, so that's an interesting thing we learned. So maybe what needs to be done is instead of putting the just make sure once again that that is indeed what happened. Go back to 50. So these are very typical examples of quirks or subtle things which might not be so obvious in an EM simulation software. So one has to be very careful, and mostly comes from experience and playing around with it and then trying to reason your way out. I would not have expected this to do it, but it's again got to do with some convention. So we'll do something strange. I'll tell you a bit now. Let's just go back here, and basically it didn't change. So obviously my attempt to change the impedance of the port to 74 ohm to make it match did not work here. So I'm going to try a trick, and it's basically going to make a sub-circuit, use the box there, and then put a different port. Right? I think this is just something to do with the convention of how microwave office calculates things. When one uses the direct EM structure or one uses the EM structure in a sub-circuit. I put my ports here. Define a common PZ. That way I can tune this and see how the overall transmission changes. Right? So this is an additional flexibility if I use a sub-circuit like this. Let's go back here and change this to schematic 2. Right, looks bad. So basically it was giving us the result of using it as 50 ohms, which is because it's same as before. Now I put it, oh, it's already there. Out my tuner. It's this one here. And there you go. It actually works. So you see that for 74 ohms, which is what we had calculated, you get decent performance. Of course, there's still a finite length and there's some finite mismatch, so you get these kind of resonances, but it'll never get worse than some number. In fact, we can, let's put this as a reference. Oops. And try to see, oops. Where does it do this? Yes. Yeah, you can compensate for lower frequencies or higher frequencies, because then it's can't really say. So I think this actually is indeed 74 ohms, because it sort of gives a nice repeatable kind of behavior which you expect for a transmission line of proper uniform impedance. So this 74 ohms was quite a good guess, and the problem was something else if we were not actually you really using a 74 ohm port. Now let's go back to this being small again, and let's see if that makes it somewhat worse or not, and then I'll explain with another example what that small or large thing actually means. Okay, I'll go back to, I guess it had gone much bigger already. So okay, let's keep it at 100. So,
when this TX line calculates this number, so it also does some EM simulation calculation, or based on?
no, it doesn't actually carry out a simulation like what we are doing. It's not that it's a front end interface and you just enter these numbers and it's actually doing the calculation. For a range of typical dimensions and parameters, you can come up with approximate solutions, which could be either analytical or some simplified numerical equations. And then those can be used. So I don't remember if Posar has a discussion on those kind of equations, but basically you can make some approximations, and using that you can come up with an analytical solution to the Maxwell's equation for computing the characteristic impedance and other things. So that's what TX-Line actually uses. Okay, let's see. I guess we will not be able to start the amplifier discussion today, but that's fine. We can finish this and start from next time. I initially was not planning to go into the slot line details, but I figured this differential port is something, at least knowing that it exists. This thing called internal port. Oh yeah. So in fact, this is even better now. So making that bigger, we had sort of made it worse. But anyway, you know, the thing is between here and here, even though in dB scale, it looks like a lot, this is minuscule changes in the overall properties of the thing. But the general idea was actually fine. It just we were stuck because of something else. So, so this is great. So this works. Now, let me show you what I meant. You know, by changing the dimension of it, what I was trying to do. One simple way of modeling it, the situation is that here is your slot line in the middle of some transmission line impedance. Let's now make it 50. It doesn't matter. I can make all of them 74 or all of them 50. It doesn't make a difference. But the point is your port is 50 ohms. This port is also 50 ohms. Your transmission is also 50 ohms. At least you've designed it to be 50 ohms. However, the connection is the problem, okay, which is essentially what we are trying to do here. We don't know exactly sort of what's going on. Now, you know, as often in science, when you're not sure, you try to come up with hypotheses. And sometimes when the underlying assumption is wrong, you can come up with all kinds of explanations like I just did 15 minutes ago. And I'm usually very good at coming up with explanations, which could all be wrong. Because our underlying assumption that there was a problem here was wrong. So the reason the return loss was bad was because the port was not being chosen as 74 ohms by changing it here. So you cannot change it in the electromagnetic simulation and directly use it in a measurement. You have to set it up in a sub-circuit like we see. Okay, so then I said that, okay, maybe this is what's happening. And even though I argued first that, you know, this is really small, it's only 50 ohms, 50 microns. 50 microns is not very long compared to the wavelength. So it really shouldn't see the mismatch of because of this piece and all. And that's why we're trying to make it wider. And the general idea here is that if you have a bit of, you know, 2D strip like this, something which is narrow and long, this can be thought of as in the simplistic case as an inductor, right? If there is a ground plane behind it, very close to it, then it's a transmission line because there's inductors and capacitors and inductors and capacitors to ground. But essentially, what we are talking about is that you have now, again, looking at a sort of a side view, you have a ground plane underneath, and then you have a metallic, and then there is dielectric, and then there is a metallic strip on top, right? If this dimension is small, you know, small enough, and the dielectric constant large enough, then it feels the presence of the ground, and then it's a transmission line. It's a microstrip transmission line, which we model like this, right? Right, this is how we model transmission line. But if this capacitance is basically not there because this distance is very small, this distance is very large, or the width of this conductor is very small, then essentially you can sort of forget that this exists, and then it's just a piece of inductor. Okay. The opposite regime is when this is very small and the width of this conductor is now, fat and wide, so it's like a square. Then you have the situation of where you can ignore this and you only have a capacitor. Okay. So this is sort of how one should think about pieces of metal lying on top of a substrate with a ground plane underneath. It can be an inductor or it can be a capacitor. Again, these are approximate models for small pieces because that it cannot be anything else. Again, we are assuming lossless everything. So it can only be a capacitor or inductor, or it can be something in between. It can be an impedance in general. So, as you know that for a long enough line, it looks like a transmission line, which can be thought of as inductors and capacitors. When we turn them with boundary conditions, it can look like an LC circuit. So all of those things, but that's sort of the general idea that if you have a strip of wire, a strip of 2D surface like this, which is thin and long, then you can think of this as mostly an inductance. Okay, and because of that, this thing here, I have to model. So this is what Supriya was saying. The port is here. So between the port and the slot line, there is some object here. How do I model it? Should I model it as an inductor or should I model it as a capacitor? The simplest always is that, okay, this is an inductor because the ground plane is far away. So I would say the capacitance is not going to be a lot, but even the inductance should not have been a lot because of the length and the dimensions involved here. Okay. That was my original intuition, but I said, well, it's not working. So I started giving other possible explanation, but clearly that was not correct. So when that is the case, then basically you can model this situation by putting an inductor here. I'm going to again create a okay. And now we want to see what happens to the transmission from one port to the other through a piece of transmission line, which has been connected to the ports with the help of these inductors. Now, depending on the exact situation of this connection, this object here in the middle could be an inductor like this. It could be a capacitor to ground. It could be an inductor and capacitor to ground, like maybe a pi section. All of those things are possible. We know that if you put a gap in the, in the conductor, like we had done before for, actually we actually never really discussed this on transmission line, but a gap is like a capacitor. So that is another way you could have a situation where you have a gap. It's like if I created if this was not connected all the way and I left it here, that's a gap. That's a capacitance. That's how you make a capacitance, in-plane capacitance in 2D circuits. Okay. So it could be anything, and then that will have an effect on how the transmission will be, and that will give you some reflections and return losses and other things like that. Okay. So just to get a feel for this, how much inductance does it take before things start looking bad? We can look at the transmission through this. Okay, so now let's duplicate this one. And by the way, yesterday somebody was asking, this is also how you can model a wire bond, right? A wire bond is something which connects two parts of a circuit, and it's a piece of loop of wire going up. So you just basically model it as an inductor in series between that. Okay. So again, I'm just going to look at S21 and S11 of this situation here. And I'm going to put a tuner on the bond inductance. So obviously the ideal situation is when this bond inductance is 0, because 0 is basically perfectly short thing. The longer the bond is, or the thinner the wire is, the larger this inductance. So that will make it worse. So small inductance, because omega L will be small, right? That's basically what matters. So now let's look at this. क्यों तंग कर रहा है? चलो उसको साइड में चलने दो. It's like I can't even open the. Because of the brilliant. I think that tuner caused multiple calls to the simulator. Brilliant. Managed to crash it. Right. Are you guys still here?
Yes.
Okay. All right. So I guess it was not saved, but not enough was deleted. So anyway, we have restored this now. 50 ohm port, 50 ohm transmission line, 50 ohm port, 2 inductive connections between the two. And I've set it to 0.1 nanohenry for now. And that's the thing. I've disabled all the EM structures so that that thing doesn't show up here. Okay. So for 0.1 nanohenry on both sides, the overall return loss is fairly good. It's below minus 20 dB, but what you can see, it's getting progressively worse as the frequency goes up. And this is what you would expect for an inductive bond, because omega L increases with frequency. So the mismatch is actually getting worse with frequency. So the higher the frequency you go to, the better. So here you don't see that kind of, there is this resonant behavior which is happening because of the finite length of the transmission line. So it's giving you these special points where the extra effect of the inductance is being compensated by the transmission line itself, and you get perfect reflection, absorption, and transmission through the system. But these are very low numbers we're talking about, okay, all below, but it gets slightly above minus 20 dB out here. And so basically you can say that 0.1 dB of inductance is okay. It's not too bad. But now if you start to increase it, basically see it will get worse, right? And typically one is working in the 5 to 7 gigahertz kind of range. So now it's starting to show some effect. Minus 16, not too bad. Let's go up to 1. And now it's no longer really that great. Okay. So 1 nanohenry of inductance is not really good as something which is bridging transmission lines like this for. So this is the reason why yesterday I was talking about that you put many wire bonds in parallel, because what does that mean? This means this, right? You put more and more wire bonds in parallel, then you have inductors in parallel, which means they get basically divided by the number of wire bonds. So the inductance goes as 1 over n. So if you put a lot of wire bonds between the two connections, then you help the situation by reducing the inductance between the two. It could increase the capacitance between the line, but that depends on whether the capacitance was very high or not. Sometimes that capacitance actually helps because we have not formally looked at other kinds of impedance transformations. So we only looked at the quarter wave transformer, but the simplest impedance transformer is actually just an LC circuit, which is sort of like a section of a transmission line, right? This actually does the job a little bit. It's sort of the fact that the capacitance is, compensating for this inductance and forms this LC, which is now a part of a transmission line. So you see, this is one transmission line, this is one transmission line, this is part of a transmission line. And if L is unavoidable, by adding a C such that this ratio of L over C is close to 50 ohms, you can actually create a match. Okay, so this is a small digression. We will discuss this in a separate class of this kind of impedance transformers to match things. Okay, so this is useful to sort of have, at the back of your mind about these numbers, how much is okay. So 0.1 nanohenry is okay, but 1 nanohenry is not. So one tries to use these rule of thumbs and remember them to figure out how much wire. So, for wire bond also, there are some rule of thumbs available that, okay, this is a wire bond which is 100 microns in diameter. So 1 millimeter of that wire will have so much inductance. So again, these are rough calculations because that number only makes sense if the wire bond is sort of isolated and straight. If it is curled and it's on top of a surface, then it will have some inductance to some capacitance to that ground plane, and then the whole situation changes. But there are these rules of thumb. Okay, so this was essentially what I was trying to see, that I thought this piece, because of our incorrect data, I was swayed to give an explanation or try something. And that's why I was making it wider this way, because then in this direction, the inductance becomes less, and the capacitance to the ground will also, in this case, of course, there's no ground, that will also would have been helped, but that was, of course, completely wrong. There was no problem. This was very small that it didn't matter. Okay, so again, a rule of thumb for strips of metal. Again, there are too many variables here, but an isolated strip of metal is just sitting on a substrate with a very wide, very sort of narrow aspect ratio, so a narrow wire and long, typically for a micron width. So if the width is 1 micron, then the inductance you get is about a picohenry per micron. So actually, it should be smaller than a micron or so, but a picohenry per micron. So if you have a 100 by 1 micron piece of wire or piece of strip, then it will approximately have 100 picohenries of inductance. That's sort of a rule of thumb. So when you're designing circuits, so Joydeep, you know this in designing your paramp devices with all those connections, because you have this DC plus AC. So that is how one estimates, and that's what one tries to minimize, to reduce the length and make them as wide as possible. Okay, so that's where these numbers come from. You can actually use microwave office simulation to check this. Make a narrow strip of wire, put it on a substrate, keep the ground planes away, just measure the transmission through it and try to match it to the response of an inductor and see what inductance you need to match the response. And basically, by doing that, you're going to get how much inductance. These things often come out to be incorrect in real-life situations, because often the model doesn't reproduce all the conditions in the system, but it gives you a reasonable idea. Sorry, there was a question. Joydeep, was it you?
No, I said okay. Yeah.
Okay, your voice is coming out to be very, very low, so I couldn't hear. I just knew that it was, you said something. Okay. Right. So I think that's probably a good place to stop. So basically, today we finished up the CPW and essentially spent a lot of time about looking at this differential port and the slot line mode. And it's also useful to know that it's difficult to make 50 ohms in a slot line. So maybe I'll just say one last thing about I mentioned briefly is that how does one make a transition from CPW to a slot line? Okay, and the way it can be done, and this is something actually I did for my PhD work. I mean, not that I invented it, I just used that design from somewhere. And the point is this: so you have from this side something which is plus, oops, right? So plus conductor, and then this is ground, right? This is ground. But this is the potential difference is being developed like this. Now, this is a 3-conductor system with 2 grounds on either side, whereas a slot line is just a 2-conductor system. So you could imagine that this can be thought of as a slot line if this was not there. Okay. So the way to do it is you start with the CPW and then slowly take one of the grounds away. Just like in the microstrip to CPW transition, you brought a ground in. So as you slowly take it away, then this, this becomes less important and this becomes more important. And you then have to adapt this something like that, and then adapt this to something like that. I mean, I'm doing a terrible job of drawing it, but you get the idea. Okay, you just morph it from a 3-conductor system to a 2-conductor and move one of the ground away, and then the slot line mode will be contained between these two. One of the major reasons for doing this kind of a transition is for differential devices which have both conductors on the top, like most devices. So in fact, the paramp type devices which I was studying during my thesis had that. So then you just had 2 things and you put your device across it, basically a Josephson junction. So it was convenient to do that. But this transformation was in fairly narrow band. It didn't work at very high frequencies, worked okay at low frequencies. You'll know that it definitely work at DC because there's no problem here. So low frequencies it works, and high frequencies it doesn't work. So I don't know, maybe this actually could be a kind of one of the projects, but it's a little tricky, but we can see. And the way you test it is you can excite using your standard connector here and through a launch, but then you can put here a 50 ohm surface mount chip or whatever the impedance is. It's not 50 ohms. You can put that here and then measure the absorption of that, and that tells you whether it works. That's one way. Alternatively, you could basically mirror image this part and then come back to a 3-conductor system, something like that, and go back to CPW. Now you basically have 2 transitions, CPW to slot line and slot line back to CPW, but now you can measure it using standard things and you can see the reflection, and then you can figure out how good the transition is in this way. Okay, so that's basically it. So is there any last few questions, and then we can stop?
So in this transition, what happens to the bottom plate? Does it
Which plate?
stop up? So there's a ground at the bottom as well.
Yes. So I guess I should have mentioned this, that this should be done usually in a CPW geometry, not in a CPWG geometry, which means that your initial CPW line should be in the regime where the presence of the ground plane at the bottom does not play a role. Otherwise, this doesn't work. If the ground plane is close by, strictly speaking, it can still work because that mode will exist. But maybe this is a good segue. I guess we will still have to continue with transmission. I was actually not planning to cover these, but they sort of form a nice story together. You come to this, and this is a coupled microstrip line. If you have a ground plane underneath, I was mentioning this earlier when we introduced slot line. If you now have a ground plane underneath, and you have this situation where you cannot ignore any of them, then you have to consider this. So then you have a situation where you have V ground, which is one potential, and then V1 and V2. So now there is a 3-conductor system, and this has 2 different modes of propagation. So if you see here in the bottom, it says even mode and odd mode. And these are basically the normal modes you can use to describe propagation through this thing. So it's not a very simple as a single transmission line. It has 2 modes you can excite for propagation. One is when V1 is equal to V2. So then, it sort of looks like an effective larger microstrip where these two have been combined, and now it is oscillating with respect to the ground. So that's one mode. That is called the even mode. So that has V1 equal to V2. And the odd one has a situation where V1 is equal to minus V2. And the ground is there, but it sort of doesn't play a role. So this V1 equal to minus V2 is the slot line type mode. Okay. If the ground plane was slowly taken away, this even mode will essentially disappear, but the odd mode would remain, and that is the slot line mode. Does that make sense? Because the slot line mode only has 2 conductors. So in the most general case of having the ground plane there, and that's fine, as long as you are aware that these 2 modes of propagation exist and you are doing the correct excitation. So, it all depends on how the wave is excited at the beginning of the transmission line. That will determine how basically here, that's not a good place to, but how at the boundary, the waves are being excited. If you use some kind of a special source which only puts a signal which such that V1 is equal to minus V2, then only the odd mode will get excited. And if you do something where only V1 is equal to V2, then only the even mode will get excited. And you can, if you do something in between, then both modes will get excited. So these are actually almost like 2 independent transmission lines coexisting on that same structure. And one has to be careful. It all depends on the boundary conditions, but these coupled microstrip lines also are very useful for various devices. In fact, one of them we will be looking at. Again, the difference between the coupled microstrip line and the coupled strip line is just the symmetry aspect. So in this microstrip, there is air on the top, and in the coupled strip line, there is uniform dielectric. And because of that, the speed of propagation in the odd mode and the even mode is the same for strip line, coupled strip line, but for microstrip it's not, because you can see that depending on the mode of the excitation, how the field lines are going to be different. So how much air and how much dielectric is participating is different. So the effective dielectric constant for the 2 modes are going to be different, and consequently means that the speed of propagation is going to be different. So that becomes a tricky situation, because now if you have, say, a certain length of line, then the even mode will have a different electrical length compared to the odd mode. And that actually puts some constraints on what you can use the microstrip for. And there's one particular device called a coupler, which is ideally designed in a strip line. But if you do it in a microstrip, you sort of don't get as good a performance because of this particular problem, because it relies on an interference effect where the even and odd mode actually have the same electrical length, and that doesn't happen in microstrip. Okay. So we will look at this in more detail in the next class. We'll finish up with this part of the thing. Any other questions?
Why did you say that the odd mode looks like the slot line? It has a conductor below.
Yes, but when you have the situation where V1 is equal to minus V2, this VG is basically 0. So all the action is between the top 2 conductors. So it's sort of the slot line is that this is where it's happening. So it's a little subtle. Basically what I'm saying is that, so, assume there is a ground below and I have this 2 conductors here. The odd mode is the one where there is a potential difference between the 2 conductors, but they're equal and opposite. So with respect to ground, the even mode potential is actually 0. You cannot do anything. And we are interested in a situation where such an excitation only connects to a device which is connected between only those two conductors, right? Now you can see that even if this was the even mode was present, you will see that any even mode excitation, which means V1 equal to V2, will not create any potential difference across this device, right? Because its two potentials are the same on either side.
Yes.
So it will actually not do anything. Whereas only the V1 minus V2 kind of situation will do. Okay. So, this is really just a readjustment of the coordinate system. You really have two potentials, V1 and V2. Instead of these two numbers, we are defining V even, which is V1 plus V2, and V odd, which is V1 minus V2. There might be factors of 2 in the definition. So in this picture, the boundary conditions and the kind of device you connect determine the effect. Okay. So the reason it's like a slot line is because in the slot line, there are only those two conductors, and it is between, the action is between those two things. It doesn't mean that the even mode is not there and the ground plane is not there. For the odd mode, the ground plane plays less of a role. Okay. So in other words, if the ground plane is slowly taken away, then the odd mode would survive, but the even mode will go away.
Even will go.
So that's why it's sort of like the slot line. Okay. All right. So we'll stop there and continue on Saturday. Okay. Right. Bye-bye.